Our topic is building clinical decision support system for cardiovascular based on knowledge graphs. I'm Xinyi.
I'm Dianchen.
The implementation so far, we first construct the sample knowledge graph topology and implement node-to-vec algorithm and get the embedded vectors. After that, we have done part of the data processing, and also we run through the dynamic time wrapping for clustering. Here's a brief introduction of our dataset. As we mentioned before, the dataset contained the basic information of patients, and with the understanding of the data, we found there exists 15,000 distinct diagnoses, which means that different patients will share the same disease with different but similar symptoms. And to be noticed is that only a few of the diagnoses over the 15,000 diagnoses are related to the cardiovascular disease. And other important attributes such as admit time provides the date and time that the patient was admitted to the hospital. Since the patient's symptoms are different, also their consultation time points are different. As a result, their corresponding duration of treatment is different. So we need to find a reasonable algorithm to organize the knowledge about disease and the associations of symptoms based on our data. To do this, we first need to construct a graph in the d-dimensional space according to the actual problem, and then embed the nodes of the graph in d-dimensional vector space. The idea of embedding is to keep connected nodes close to each other in a vector space. In our case, the nodes can be either represent the disease or the symptom, and the edge represent the relationship between each node. So the reason why we choose node-to-vec is that the results are weighted in the homomorphy and structural equivalence of the network by adjusting the weight of the random walk. Specifically, the homomorphy of the network means that the embedding of nodes that are close to each other should be as similar as possible. For example, in this slides, the first picture represents the depth first search. The embedding expression of a disease node and its connected nodes, such as symptoms, should be close, which they are in the same color. So this explains the homomorphy. And also for the second picture, explain the BFS, which is the breath first. The symptoms can lead to other disease, such as we know that the symptoms can lead to other disease. To explore this, we want the result of graph embedding to express the structural equivalence of the network. The progress of a random walk needs to be more inclined to BFS by adjusting the parameter of the model, since BFS will be more inclined to go through multiple jumps to a distant nodes, so that the generated sample sequence contains more information about the overall structure of the network. And here is the node-to-vector result.
Here's our implementation and result of node-to-vector algorithm. Firstly, we construct a sample node-to-edge topology. The first column represents the number of the first node. The second column is the number of the second node. We could construct the third column to represent the weight, but here we assume that the weight of each relationship equals to 1. And in the right part of this slide is the result of embedding. Here we choose the number 1000 node, and we can see that it was represented by a long vector. In this picture, we can see that we use 16 kinds of disease, and similar disease are located in neighboring locations. And that is this space are distributed into 16 species. Here is the dynamic time warping algorithm. This algorithm is to compute the distance matrix of the diagnosis sequence of different patients, since the time range of every patient is not similar. And we still have many challenges. First is that we just use the sample data to implement the node-to-vector algorithm. So we need the actual knowledge graph structure to get more accurate results. And second is that we need to update our cardiovascular dictionary for data preprocessing. Since the dataset contains several kinds of disease, and we are only focused on cardiovascular, so we need to extract the cardiovascular records of these data sets. So we need to update our ASVD dictionary to do this part of job. And third is that we need to train an LSTM model with attention to predict the probability. That is, for each patient, we need to predict the possibility for him of getting the cardiovascular. So that is our presentation. Thank you.
Thank you.